Okay, so after all that excitement, we'll get down to some real work. So I would like to give you an understanding of how a blood sample is processed to provide the results given as part of the full blood count. I'm going to present some general principles, but different analysers may differ in their detail. But I just want you to have a broad understanding of the process. I mentioned that we do more than 800,000 full blood counts per year in UHL, and so this has to be a largely automated process. So, what do we get out of a full blood count? What is a full blood count? Well, the analysis provides us with information on the haemoglobin concentration within the blood, and about the red cells themselves, including the size, number, and the amount of haemoglobin in each cell. We get information on the number of platelets and information about the size, distribution of platelets. And finally, we get the total white blood count, and analysers are also able to give us the numbers of neutrophils, eosinophils, monocytes, lymphocytes, and basophils. And this is known as the 5-part differential count. To get information about individual cells or platelets, we need to make sure that the blood we're analysing isn't clotted. So full blood count tubes contain an anticoagulant, and this is usually potassium EDTA, which acts to chelate calcium ions. Calcium ions are crucial for blood clotting process, and so removing them means that the blood shouldn't clot. However, it's very important to ensure that the right amount of blood to EDTA ratio is present. If there's too much blood, the sample may clot, but if there's too little blood, and so there's a higher proportion of EDTA, this may affect the way the cells appear when they're examined under a microscope. The bottles are vacuum sealed to allow the right amount of blood into them, but there's also a mark on the side of the bottle. The analysis is undertaken using a closed system. A small capillary tube from the analyser is inserted into the sample, into the centre of the sample, and a determined amount of blood, a standard amount of blood, a sample is taken and analysed. So how is haemoglobin measured? Well, remember that the haemoglobin resulted is a concentration and not an absolute amount. And so the units of haemoglobin are grams per litre. From the 1st of March 2013, there is a move to standardise the reporting of haemoglobin units as grams per litre across the UK, and this is a part of pathology harmonisation. We measure the haemoglobin concentration using a method of spectrophotometry, and this is based on the Beer-Lambert principle, which states that the amount of light absorbed by a solution is proportional to the amount of absorbing chemical in the solution and the path length of light. But the path length of light will be standardised within an analyser, and so essentially we can say that the amount of light absorbed in a given volume of solution will be proportional to the amount of haemoglobin in that solution. So we take a given volume of blood and we add hypotonic solution. So the biconcave cells swell and burst to leave a solution of free haemoglobin. Now within our blood there are smaller amounts of haemoglobin. Apart from oxyhemoglobin and carboxyhemoglobin, there are small amounts of haemoglobin such as methemoglobin and sulfhemoglobin. And so to measure accurately the total amount of haemoglobin, we need to convert it to one form. The standard method for doing this involves converting it to cyanohemoglobin by the addition of potassium cyanide. Though many analysers use other chemicals nowadays to convert the haemoglobin to a single form. The analyser then takes the aliquot of free haemoglobin and shines a light of known wavelength through it. The wavelength chosen is one that we know will be absorbed by haemoglobin. We can work out how much light is transmitted through the solution, and hence the amount that's absorbed. The haemoglobin concentration can then be worked out using information from a control curve, and this is done automatically by the analyzer. For information about individual cells, analyzers use a process called hydrodynamic focusing to make a single stream of cells 1 cell thick. The single stream is then passed through either a beam of light or an electrical current. And so as each cell passes by, either the light will be scattered or the current will be impeded. And this can be measured. And so the red cell count is simply calculated by the number of times the light or the electrical current is interrupted. And this is given as a number of red cells within an aliquot as 10 to the 12 per litre. The amount of light scattered or electrical current impeded is directly proportional to the size of a cell. And so we can work out the mean cell volume within an aliquot of blood. Putting together information from all the cells within that aliquot, we can plot the distribution of sizes within the sample. And this should be normally distributed. And so if you have changes in the shape of the normal curve, it can give you information to tell you if there are perhaps small cells there, or perhaps if there are lots of cells of different sizes. And this is called the red cell distribution width. And it can be given as either a coefficient of variation, which is presented as a percentage, or a standard deviation. The mean cell haemoglobin gives us information about the average amount of haemoglobin in each red blood cell, whereas the mean cell haemoglobin concentration gives us information on the concentration of haemoglobin in a given volume of packed red cells. The mean cell haemoglobin can be measured by either spectrophotometry of individual cells, or in some instruments it's calculated by dividing the haemoglobin by the number of red cells in a given volume. The mean cell haemoglobin is an amount, and so is given as picograms or 10 to the minus 12 grams. The mean cell haemoglobin concentration is a calculated parameter derived by dividing the haemoglobin by the product of the mean cell volume and the red cell count. You can imagine if there have been any incorrect measurements in any of these parameters, then this will affect the accuracy of the MCHC. And certainly in Leicester, we've stopped reporting the MCHC. It's the least useful of all the parameters. The hematocrit, or packed cell volume, these terms are used interchangeably. And to explain what these mean, I'll explain to you how the parameters were derived manually. And essentially what used to happen was that we would take a column of blood into a capillary tube of known bore size. We would spin the column for a standard time at a standard speed, and this would separate the blood into the red cells and plasma, separated by a small buffy coat of white cells. The packed cell volume was the ratio of the height of the red cells compared to the total height of the column. Of course, this isn't done now in Analyze, and instead it's another calculated parameter. So the hematocrit is a product of the mean cell volume multiplied by the red cell count. To measure the reticulocyte count, we use the fact that reticulocytes, unlike mature red cells, retain ribosomal RNA. And so we use a fluorescent dye which binds to RNA and fluoresces when the cells pass through a laser beam of light. And so it's possible to calculate how many reticulocytes there are in a given volume of blood. Remember that the number of red cells far exceeds the number of white cells. To analyse white cells, we need to first lyse the red cells. The total white cell count can be measured by light scatter or impedance. But to identify the number of the different white cell types, we again bind a dye to the cells, and the dye that we use in our instruments in Leicester is myeloperoxidase. Different types of white cells will bind myeloperoxidase to different degrees. And then, as the cells pass through the laser beam, we can pick up information on the amount of myeloperoxidase bound to the cells, and also we can get information on the size of cells. And taking that together, we can plot a graph to identify different subsets of white cells. So, for example, lymphocytes are very small cells which don't bind myeloperoxidase very easily. And neutrophils are larger cells which bind lots of myeloperoxidase. This graph isn't an accurate representation of what the analyzers produce, but it just simply shows the principle. Basophils have slightly different properties, but they're analysed in a similar method, but just in another channel. Analysis of platelets depends really on the size difference between red cells, which on average about 8 micrometers in diameter, and platelets, which are about 2 to 4 micrometers in diameter. So the number can be measured by light scatter or impedance, as I've shown previously for red cells. And similarly to red cells, we can also get information about the size distribution. There is a small crossover between small red cells and large platelets. And this can make the count less accurate if there are lots of very large platelets or red cell fragments in the sample. Results which are outside of the normal range, or where there are cells that the analyzers are unable to identify, or if there are immature cells in a sample, the analyzer will flag the sample for a blood film. A biomedical scientist will review the results and decide if a blood film should be made. If a film is made, it's examined under a microscope, and a small proportion are sent through to the haematology doctors to add a medical comment. Okay, so I hope you have now a better understanding of what's meant by a full blood count, and of the principles that are used to derive the parameters that are measured.